Hi everyone, welcome back to chemistry. In this video, we're going to talk about 6.5 in your textbook, which is mass-to-mass problems and also limiting reactants and percent yield. So we'll talk about what all those things mean, but for now, let's talk about mass-to-mass problems. So in previous videos, we learned how to go from grams of some substance A to moles of some substance A, and that's using the molar mass as a conversion factor. And then we also talked about how to get from moles of substance A to moles of substance B using the mole ratio as a conversion factor. And now we want to talk about how we can go from grams of A to grams of substance B using kind of all of the information that we've learned in the last few videos. So it sounds like a lot, but after a while it gets pretty methodical. So just stick with me here. And let's try out an example. So this example says how many grams of sodium chloride are produced from 40.2 grams of sodium. So I always, as usual, like to kind of have a problem breakdown. How am I going to solve this problem? So it looks like I'm going to start with grams of sodium, and we know how many. So I'm going to start with grams of Na, and I want to eventually get to grams of NaCl. So note, right, these are two different substances. So we need to kind of think about, okay, we can't go straight from, grams to moles and then back to grams. We got to do the mole ratio at some point to get from, substance A to substance B. So let's try this out. So I know I can't get straight from grams of Na to grams of NaCl in one step, but I can probably go an alternative route. So I know how to get from grams of Na to moles of Na, right? And I can use my molar mass of Na for that. And then I know how to get from moles of Na to moles of NaCl, right? Using my balanced chemical equation. Or let's just say using our mole ratio, because we have an easier way of saying that. Mole ratio between those two things, Na and NaCl, right? Because we have a balanced chemical equation here. And then we know how to get from moles of NaCl to grams of NaCl using what? Yeah, the molar mass again. This time, the molar mass of NaCl. Okay, so we can't go this way just in one step, but we can, like always, go this kind of alternate route, and that's what we're going to do. So let's try this out. So we start with 40.2 grams of Na, so that's going to be the first kind of train track I write here. Remember to have your units and also the thing that you have, right? That's going to actually make your life easier when you solve these, I promise. All right, so we know we're going to have quite a few train tracks here, so because we've got a lot of steps. So first step, though, just kind of breaking it down. We want to get from grams of Na to moles of Na. So grams of Na to moles of Na. And we said what connects those things is the molar mass of Na. So first we got to figure out the molar mass of Na. So let's go over here, and we'll write ourselves like a side note that the molar mass of Na equals... we only have one sodium atom, so it's just going to be the mass on the periodic table, so 22.990. Remember, that's in grams per mole. Okay, we can break that number into two conversion factors where we have grams on top and 1 mole on the bottom. So we'll do that. Let's see. Let me zoom out here. So we'll do we want grams on the top or the bottom here? Yeah, we want the grams to be on the bottom because we want to cancel them out to end up with moles. So we're going to put 22.990 grams of Na on the bottom. And how many moles of Na on the top? Yeah, 1 mole, right? Remember, our molar mass is always grams per 1 mole. I know, you're probably so sick of me saying that. But sometimes it can be confusing. Okay, so that's great because that cancels out our grams of Na. And now we're in moles of Na. So from moles of Na, we said we want to get to moles of NaCl next. So how do we do that? We said, okay, the thing that's connecting those two is our mole ratio given from our balanced chemical equation. So we have, let's see, looks like we have 2 moles of Na reacting with 1 mole of Cl2 to give us 2 moles of NaCl. So what's the mole ratio between Na and NaCl? Yeah, it's a 2-to-2 ratio, right? 2 moles of Na go in, and 2 moles of NaCl come out. Now, why did I put moles of Na on the bottom? Yeah, to cancel it out, right? I've got moles of Na over here and moles of Na here, so I want to cancel them out, so I'm left with the thing I want to get to, which is moles of NaCl in this step. All right, we're still not done because we were asked to get to grams of NaCl, so we're not quite there yet, but we are close. So let's see, we got one more train track, I think. So we got, now we got to figure out the molar mass of NaCl, because what's connecting moles of NaCl to grams of NaCl? That's going to be the molar mass of NaCl. So let's calculate that over here, molar mass of NaCl. This time a little less straightforward, but that's okay. We have one Na atom and one Cl atom. So Na we said was 22.990 grams per mole, and Cl is 35.453 grams per mole. Right now we got to total those up, so 35.453 plus 22.990 is going to give us 58.443 grams per mole, and that equals the molar mass NaCl. All right, so now we have moles of NaCl on the top of our previous conversion factor. So where does moles of NaCl need to go now? Yeah, on the bottom. So 1 mole of NaCl is going to equal 58.443 grams of NaCl. And then we can cancel out those moles of NaCl, and we're left with grams of NaCl, which is what we wanted to get to, right? We wanted to get to grams of NaCl in the end. So we're at the last step. All right, so now that we've actually converted to grams of NaCl, right, we've got our grams of NaCl in the top right of our entire conversion factor problem, which means that's what we're left with at the end of this problem. Now we can just go ahead and do the calculation. So it's a lot, but the way I like to think of it is multiply everything on the top and then divide by the product of everything on the bottom. So what do I mean by that? That's just reminding you guys to use PEMDAS on the bottom here, and divide those two numbers, or multiply those two numbers on the bottom together, and then divide by the product of those two. So let me show you that in 2 steps. So 40.2 times 2 times 58.443 gives us 4,698.8, 172. Then we're going to divide that big number by 22.990 times 2. So I have parentheses around these two numbers here for my denominator, okay? So that's going to give me 102.19263 grams of NaCl. All right, so now let's make sure we've got the right number of sig figs. So we've got 3 sig figs in our measured value. And then we've got our molar mass here, which has 5 sig figs. This is a ratio, so it's exact. And then our last molar mass also has 5 sig figs. So we're going to need to round to the lowest number of sig figs, which is 3. So looks like we'll want to round to this digit here, which is going to give us 102 grams of NaCl. All right. And that's going to be 3 sig figs, so I'm just going to note that there, and then box it off because it's our final answer and we are confident. All right, so let's keep moving along here. So this is how we go from grams of one thing, right, grams of substance A, to grams of substance B, using conversion factors that we actually already know, right? It is difficult, right, because we're putting all of these things into one problem, but just kind of break it down step by step. That's my biggest tip. Okay, let's practice this again. So this says how many grams of C2H4 are needed to produce 56.7 grams of CO2. Okay, so grams of CO2 is what we start with, some substance A. We want to get to grams of something else, substance B, right? Grams of C2H4. All right, so in order to get from grams of CO2 to grams of C2H4, well, we know we can't do that in one step. But we can go an alternate route. So we want to go from grams of CO2 to what? Well, the only thing that's going to connect some CO2 and C2H4 is our balanced chemical equation and the ratio those two react in that equation. So that's our mole ratio, right? So we need to go through moles in order to get back to grams. So we got to go to moles of CO2, and we're going to use our molar mass of CO2 to do that. Then we need to go from moles of CO2 to moles of our other thing, right, C2H4. And that's going to be using our mole ratio. And then we want to get from moles of our other thing to grams of our other thing using, right, the molar mass of that other thing, C2H4. Okay, that's what's connecting each of those pieces. Okay, so again, I know it's a lot, but break it down, right? Let's just think about this first step first. So we want to go from grams of CO2, and how many grams do we start with? Yeah, 56.7 grams of CO2. So that's our first kind of conversion factor. Then our next one is going to be the molar mass of CO2, right? Because that's what connects grams and moles of CO2. So we're going to have some number here of grams of CO2, and we got to figure what that is. And then 1 mole of CO2 will go on the top. So let's do our side note and figure out what the molar mass of CO2 is. Looks like we have 1 carbon and 2 oxygens. Carbon has a mass of 12.011 on the periodic table, and that's grams per mole. Oxygen has a mass of 15.999 grams per mole. So once we figure out that calculation, that is 44.091 or 009 grams per mole. So we're going to put that in here, 44.009 grams per every 1 mole. All right, next one. Now we're on the second step, which is moles to moles. How do we get from moles of one thing to moles of another thing? Yeah, mole ratio. So we got to look at our balanced chemical equation. We got to say, okay, moles of CO2 is going to go on the bottom because we want to eventually cancel it out, right? And moles of our other thing, which looks like C2H4. All right, so what is the ratio between those things? So only looking at C2H4 and CO2 right now, looks like 2 moles of C2H4 go in and 4 moles of CO2 come out. So that is the mole ratio for those two things. And now I can cancel out moles of CO2 and I'm in moles of C2H4, which is great because that's that much closer to grams of C2H4. How do we get from moles of grams of to moles of one substance to grams of the same substance? Molar mass, this time of C2H4. So C, we've got 2 of them this time, each with 12.011 grams per mole as their atomic mass. Oops, this should be H. Hydrogens, we've got 4 of them. And those have a mass of 1.008 grams per mole each. So we got to do some calculating here. It's going to give us 28.054 grams per mole. So we've got, let's see, we need moles on the bottom. 1 mole of C2H4 goes on the bottom. And what goes on the top? Yeah, 28.054 grams. Oops, let me give myself a little more room here. C2H4 on the top because we want it to end up in grams of C2H4, so it's going to be on the very top right of our conversion equation. We get to cancel out those moles of C2H4, and now our final answer is going to be everything on the top multiplied together divided by the product of everything on the bottom. Okay, so that is 56.7 times 2 times 28.054. We're going to divide all that by parentheses, 44.009 times 4 end parentheses. And that's going to give us 18.072 ... grams of C2H4. Let's do our sig fig check. So we have 3 here, 5 here, 5 here as well. And this is exact, so we can kind of ignore it. So that's going to mean we need 3 sig figs in our final answer. That's this digit here, so we'll look to this digit and say, okay, that's greater than 5, so we got to round up. So that equals 18.1 grams of C2H4. So if we want to make 56.7 grams of carbon dioxide, we have to put in 18.1 grams of C2H4. That's the ratio of this reaction. All right, so now we need to talk about something called limiting reactants. So the limiting reactant is whatever reactant that is used up first in a reaction. Whatever reactant that is used up first in a reaction. So remember, we have reactants on the left before the reaction, right? And then we react those together and we make products after the reaction. So the limiting reactant is always going to limit the amount of product that forms, right? If we use up some of our reactant A, some of our generic reactant A, if we use that up, there's no more of A to react with B, and we can't make C, right? So that's the limiting reactant. This always sounds a little funky at first, so let me give you like a scenario. So say you wanted to make some peanut butter and jelly sandwiches, and you have, for each peanut butter and jelly sandwich, the perfect ratio is that you put in 2 tablespoons of peanut butter and 1 tablespoon of jam, and that makes 1 sandwich. Otherwise, you can't eat it. You don't like any other ratio than that. That's your favorite ratio. And you want to know, okay, well, how many sandwiches can I make if I only have 5 tablespoons of peanut butter and 2 tablespoons of jam? So here's my recipe, right? And I want to know, okay, well, I don't know how many sandwiches I can make, but I know I have this much of each of those things. I have that much peanut butter and that much jam. So I want to know, all right, well, how many sandwiches can I make? And then which ingredient is going to limit the amount of sandwiches? So is my peanut butter going to limit how many sandwiches I can make, or is my jam going to limit how many sandwiches I can make? And whichever one limits the amount of sandwiches, maybe I can go to the store and get more of that ingredient. So let's see this in action, and then I'll give you some helpful tips. So it says, consider the reaction below. If a chemist starts with 5.2 moles of sodium and 3.2 moles of chlorine, which reactant limits the amount of product? So here's my peanut butter sandwich, peanut butter and jelly sandwich in this reaction, right? It's my product. And we want to know, okay, if I have some known amount of sodium and some known amount of chlorine, which one limits how many NaCl's I can get, how much of my product I can make? So let's start. We start with what we're given. And what you're going to do is you're going to set up actually 2 big conversion factor problems. So I'm going to start, we want to compare, right? So for Na, we have 5.2 moles of Na. And for Cl2, we're going to have 3.2 moles of Cl2. Right? Setting up 2 different conversion factor problems, 2 separate problems to figure out which one independently, right, limits the reaction. Which one is going to limit how much of my product I can get out. And that'll be called my limiting reactant. Okay, so starting just with Na for now, we'll just look at the yellow. So I'll actually color code this. So just looking at Na, we start with 5.2 moles of Na, and this is just going to be any conversion problem that we've solved so far, right? Start with what you're given and figure out, okay, where do I want to get to? And then you got to know what connects those 2 things. So for this one, right, we start with moles of Na, and we want to get to NaCl. In this problem, it doesn't say specifically, it doesn't ask for how many moles or grams or how much of your product you can make. It just wants to know which reactant limits the amount of product. So we just need to get to maybe moles of NaCl for each of these conversion factor problems so that we can compare, okay, well, if Na makes, 5 moles of NaCl and chlorine makes 2 moles of NaCl, then I know which one is my limiting reactant, right? And I don't even have to figure out how much of my product I can make. Okay, so for this problem, I'm going to say we just need to get to moles of NaCl. and make our lives easier. So how do we get from moles of A to moles of B? Mole ratio, right? We've got a balanced chemical equation that relates these two things, so we can figure out, okay, how do I get from moles of Na to moles of NaCl? Using my mole ratio. So we want moles of Na on the bottom, right, because we want to cancel that out and end up with our product, which is NaCl. So we'll put moles of Na on the bottom and moles of NaCl on the top. All right, now how many moles of Na make how many moles of NaCl? Yeah, using our balanced equation, we see that the ratio these two things react in, our mole ratio, is 2 moles of Na go in and 2 moles of NaCl come out. All right, and then we can cancel out our moles of Na, and we're left with moles of NaCl. All right, so it looks like it's just going to be 5.2 moles of NaCl. All right, so if I put in 5.2 moles of sodium, I will get out 5.2 moles of sodium chloride. All right, but how many moles of sodium chloride am I going to get out if I start with this many moles of chlorine or Cl2? Well, let's see. Now we're looking at just the blue. So let me color code this. So blue. We want to know how much NaCl we can make. So again, the thing that connects moles of Cl2 this time to moles of NaCl, our product, is our mole ratio. So we want moles of Cl2 on the bottom and moles of NaCl on the top. How many moles of each of those? Well, that's given by our chemical equation, our mole ratio. So we put 1 mole in of Cl2 and we get out 2 moles of NaCl. All right, so chlorine, if we put in 3.2 moles of chlorine, we will get out 6.4 moles of NaCl. So even though we're starting with less of our chlorine, right, 3.2 moles versus 5.2 moles, even though we're starting with less, chlorine is not the one that limits how much product I can get, because we make more with chlorine, right? It's actually sodium. Sodium is limiting the amount of NaCl I can make. So in this reaction, if I start with these amounts of my reactants, the most I can make of my product before I run out of sodium is 5.2 moles of NaCl. I can't make 6.4 moles of NaCl because I'm going to run out of sodium first, right? Okay, so we would call sodium, Na is our limiting reactant because it's going to be used up first. Because we will use it up first. We will also call 5.2 our theoretical yield. And we'll have more on that in a little bit, but I want that to be in your notes so that you know with a worked example how to get to your theoretical yield. But we'll explain it in a little bit. But that's your theoretical yield. That's how much we can theoretically make of NaCl if we start with these amounts of our reactants. Okay, so now I want to give you just this quick slide of how to determine the limiting reactant. These are just some tips. So now that we've seen one worked example, the first step is to balance the chemical equation for the chemical reaction. So if you were given, this chemical equation, but it wasn't balanced yet, in order to get your mole ratios, you have to have a balanced chemical equation, right? So you got to balance first. Second step, convert the given information into moles. If you're just trying to figure out the limiting reactant and you don't need to know how much of your product you're making, you can just convert to moles. And that way, right, you can compare moles to moles for your reactants. If you wanted to, you could go all the way to grams, okay? But you don't have to if you're just trying to figure out which reactant limits the product. All right, so sometimes we want to know in lab what our percent yield is. So reactions that are performed in lab, they're never perfect. So we make mistakes, right? We might spill a little bit of a liquid or we lose some solid while we're transferring. Sometimes things stick to our beakers and we don't even realize it, right? And sometimes we just don't finish a reaction because there wasn't enough time, or we didn't put enough heat in before we had to leave. So in order to figure out, okay, well, right, how good was my reaction, you need to calculate the percent yield. And that's given by this equation here. Okay, so percent yield equals actual yield over theoretical yield times 100. And let's just break this down a little bit. So the actual yield, this is how much of your product you actually made. So after your reaction, how much of my product did I actually get out? Your theoretical yield, which I mentioned that we would talk about more, is how much of your product, sometimes I'll abbreviate product PDT, you could have made if everything went perfect. That doesn't happen, right? We're human, we make mistakes. You can get pretty close to 100% of your yield, but you're not going to make exactly 100%. So going back to my reaction up here, say I'm in lab, and I already calculated that sodium was our limiting reactant. I can only make 5.2 moles of NaCl. And usually in lab, you're going to convert that to grams, but we know how to do that, right? We can use our molar mass. But I can only make 5.2 moles of NaCl, and that is if I do everything correctly, right? But say I spilled a little bit of Na, and I had even less of Na to start with, and I actually got, 3.2 moles of NaCl at the end. Well, then I would need to figure out what my percent yield was. And that's where this calculation comes in handy. Oh, and then the times 100, sorry, I skipped over that. The times 100 in this equation is just to puts your answer into a percentage. It just takes the decimal that you're going to get from dividing these two numbers and puts it into a percent form. You're just converting from decimal to percent, or fractional value to percentage. Okay, so your theoretical yield, let's practice this. So you have to calculate your theoretical yield because you got to figure out how much you could make theoretically if everything goes according to plan. So let's try this out. So in the reaction below, same reaction as before, sodium is the limiting reactant, right? We figured that out. We figured this out. If we start with 3.4 grams of Na, how many grams of product could form? How many grams of product could form? So again, only looking at Na and NaCl. But now, note, we're starting with a different amount. Our limiting reactant for this reaction is still sodium. So we start with 3.4 grams of Na. And we want to get to grams of NaCl. So grams Na to grams NaCl. We know how to do that now. We've been practicing it quite a bit, so let's do that. So first, we want to get to moles. We got to go through moles first, right? So we need to use our molar mass, right? Molar mass of Na. And that's just going to be 22.990 grams per mole. So 0.990 grams of Na is in every 1 mole of Na. Okay, going from grams to moles of Na so that we can use our mole ratio. All right, now we're in moles of Na, and we want to get to moles of NaCl, right? Moles of our product. So we'll go, 2 moles? 2 moles of Na on the bottom produces 2 moles of our product, and oh my gosh, can't write right now. NaCl on the top. All right, we're going to cancel out moles of Na. And now we're in moles of NaCl. Now, we stopped here when we tried to figure out our limiting reactant, but this question specifically asks for grams of your product. So we want to do one more step, but that's okay. We know how to do it. So now we need something that connects moles of NaCl to grams of NaCl. We know that. That's going to be the molar mass of NaCl, which actually we already calculated above, way at the beginning of the video, which was 58.443. So let's do this. We got 1 mole of NaCl and 58.443 grams of NaCl. And now we're left with grams of NaCl in the very top right, which is great because we wanted to end up in grams of NaCl, grams of our product. All right, so let's calculate this out. And we're going to get 8.64 grams of NaCl. Actually, let's round that to 8.6 because we only have 2 sig figs here. 8.6 grams of NaCl. And that's how many grams we could theoretically make of our product if we start with 3.4 grams of Na. And if everything goes according to plan. So, theoretical yield. If everything goes according to plan, we're 100% perfect when we carry out this reaction. We can make 8.6 grams of NaCl. Now, say we actually perform that reaction in lab and we weigh our product and we actually only made 5.62 grams. We performed that in lab and we made only 5.62 grams. Let's calculate the percent yield. Said from above that we could make 8.6 grams of NaCl. NaCl equals our theoretical yield if everything goes according to plan. Everything did not go according to plan, clearly. We lost some, so we only made 5.62. So in yellow, that's your actual yield, and we'll put our theoretical in blue. So we've got our percent yield equals actual, which was 5.62 grams of NaCl, over our theoretical, which was 8.6 grams of NaCl. And then we got to multiply whatever number we get out of that division by 100. Looks like after I carry out this calculation that I'm going to be at percent yield of about 65%. Which means what? That means for this reaction, we made about 65% of our product that we could have. Okay? Our percent yield for this reaction was 65%, which is actually not too bad, especially for in a Chem 121 class.